As we discussed, only applying the IBIS model is insufficient for a signal integrity SI engineer to evaluate the link budget. Therefore, we show you why you need an enhanced behavior model, which is the IBIS-AMI model. Let's start with the summarized image of why you cannot apply the IBIS model for high-speed SERDES under a high insertion loss. First, the SI issue from the insertion loss is a big concern. Without the proper waveform, or the I after the equation, and the RX output, not the RX input, there's no way to analyze if a link has enough margin in the link budget. Since a high insertion loss, we may want to add the TX-FFE, RX CTOE, and RX DFE modeling on top of the IBIS model. Second, the TX clock jitter information was not included in the TX IBIS, and the CDR jitter or jitter tracking behaviors were not included in the RX IBIS model either. Therefore, the SI engineer cannot evaluate the I width of the phase error between the input data and the RX sampling clock for different channel profile precisely. Third, the long simulation time of the IBIS model is too slow to evaluate a very low bit array at a high confidence level. Lastly, the IBIS model cannot emulate the link training process properly, and the real link initialization in sequence was not verified properly to make sure all the link specification can be met to establish the link in the SI design phases. Then we know what we need now. The first simple implementation is the TX-FFE. As you can see, the TX-FFE is just a finite impulse response FIR implementation, which has a few delayed versions in one UI duration of the input waveform and is added together with the proper weights or called tap coefficient. Please be advised that even though each tap coefficient could be positive or negative, the total output swing of the all tap coefficient must equal 1, which is limit to the maximum supply headroom. So, a simple superposition mathematically would generate the FIR or FFE easily, and that's a simple demand of the algorithmic modeling interface AMI on top of the IBIS. In addition to the TX-FFE, how do we handle the RX DFE? Think about the infinite impulse response IRR image for 5 seconds. Bingo! The IRR superposition is close to the FIR, but it takes the output as the unit delay elements. Therefore, it may require a few application or calibration iterations to get the residual ISI minimized by finding the optimal coefficient depending on the optimized algorithm, which should be integrated well in the AMI modeling as well. But how do we handle the error block of the EQ like the CTOE? Think about the superposition one more time for 5 seconds. Bingo! To make sure the superposition works in the modeling, we must make sure the system is linear, which may be true for CTOE. If not, the CTOE design was poor and must be improved with any linearization over VGA AGC help. In addition, we not only make sure the CTOE output swing magnitude is linear, but also the phase is linear or constant group delay. If we could make those analog blocks fairly linear in design, the behavior model of a single pulse response with a superposition in time should represent the SPICE model well enough. Then, what you need is to characterize all the CTOE equalization curves in high-pass response to a group of time domain single-pass response SPR, such that either the FIR or IIR response represents it through the AMI. Please be advised that the beauty of such simple AMI with the SPR is the fastest simulation time, such that greater than 1 million bits of the data can be verified accurately for extreme low bit error or long PRBS patterns. Alright, we will deal with data pattern pretty well for the equation and simulation time. Let's check the clock path. The first simplified clock path may be the TX jitter, which includes the unbounded random jitter Rj, bounded determinant jitter Dj, in periodic jitter Pj, duty cycle distortion DCD, and ISI. Not only the first Rj can be added easily through the random generator in floating-point number format, but also the DJ, PJ, and DCD can be injected through mathematical equation easy in AMI modeling. Therefore, the actual clock jitter can be modeled in the TX clocking. How about the RX recovery clock jitter? Let's review what the clock data recovery CDR should achieve in a series or C-link. For example, the TX clock information is embedded in the serial data, and the RX needs to recover the clock from the incoming data waveform and use the recovery clock to sample and recover the data without any bit errors. So there are a few most common system scenarios we discussed before. First, in the source synchronous system, the input data has the same frequency as the local RX clock and has only a fixed or constant phase offset, which is easy to recover to tune either at the TX or the RX side. So, such a simple phase tuning or deskew for CDR should be easily modeled or added at the TX data phase deskew. What's next? Second, in the mesosynchronous system, even though the frequency is the same between the TX and RX, the phase difference will vary from time to time, and a simple phase deskew is not enough. Hopefully, the simple phase tracking behavior of the band-band CDR model can be implemented based on the phase comparison between the input data and output clock. Also, the AMI can help model the frequency response of the phase correction or tracking behavior, which can help the SI engineer evaluate the jitter tolerance JTAL performance versus different signal integrity scenarios. Alright, looks like the zero frequency offset is easy in the CDR modeling. If not, what can we do? Third, in the plus-cross system, even though the frequency is not the same between the TX and RX, the frequency difference will be very small. For example, plus or minus 50 ppm maxima in most scenarios, which mainly confound the frequency offset between different crystal oscillators. Therefore, the CDR should be designed with a second-order loop to correct the frequency offset. Then, the AMI should add this simple model easily to capture the tracking behavior of the frequency offset well enough, which also helps the SI engineer evaluate the jitter tolerance jet-out performance versus different signal integrity scenario precisely. Lastly, the AMI can model the link training process properly, since all the digital logic can be added to the modeling, which the simple IBIS did not. Again, the SI engineer may need to verify the link training for PCIe, USB, Ethernet, etc. protocols, such as the settings of the TX-FFE, RX-CTOE, and RX-DFE can be optimized for different links insertion loss, reflection, or return loss, crosstalk, or isolation impairments. Those link impairments should also be modeled properly in the multiple S-parameter models of package, socket, daughter board, connector, backplane, or cable. Here are a summarized image showing you why you need IBIS-AMI model for SerDes or any wireline C-link. By adding the algorithmic modeling interface AMI on top of the IBIS, the enhanced IBIS-AMI model can make the signal integrity SI verification or design accurate and quick for several goals. The most critical one is to emulate the second link training process over different protocols to make sure the link impairments can be mitigated to have enough margin for the error-free target. The first straightforward link impairment is the insertion loss, in which the TX-FFE, RX-CTOE, and RX-DFE can be tuned to optimal setting to minimize the ISI through the AMI modeling. However, the link may have an impedance mismatch or discontinuity issue, which may not set the TX-FE or RX-CTOE in the best settings in the insertion loss only impairment. Therefore, adding all the S-parameter model in the link can also include a reflection impairment if it's optimized SI in the design good enough. On top of that, the crosstalk between the lengths could reduce the bit error margin, which must be verified by the IBIS-AMI modeling. Second, we care about a very low bit error, and we must quickly run multi-million bits in the SI verification, which can modeled with a time domain single pass response at super precision in time in the IBIS-AMI. The last one is the timing margin, which relates to the phase error between the input data and the assembly clock, which dynamically track the input jitter or phase movement, or even the frequency offset. Therefore, not only the TX clock jitter, but also the IX clock jitter tracking can be modeled easy in the IBIS-AMI to finalize the bit error evaluation precisely and quickly. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be better from it.